Welcome to another deep dive, everyone. This time, we're going small, like really, really small. We're talking nanocatalysis.
Smaller than small.
Exactly. We've got this super interesting university lecture here all about how nanocatalysis could, well, change the world.
It has that potential, that's for sure.
Okay, so to kick things off, what exactly are we talking about when we say nanocatalysis?
At its core, it's using these tiny, tiny particles, nanoparticles, to make chemical reactions happen faster, way faster.
So like speed boosts for chemistry.
You could say that, but it's more than just speed. With nanocatalysts, we can actually tweak them to be super specific.
Specific how?
Like change their size, their shape, even what they're made of. And by doing that, we can control exactly what reactions they help with.
Wow, it's like custom-made chemistry tools.
Yeah.
But I'm guessing this isn't just some cool science experiment, right? This ties into sustainability somehow.
You got it. Nanocatalysis is basically a cornerstone of what we call green chemistry. Less waste, less energy, using resources we can actually renew. It's pretty amazing.
So, better for the planet and better for industry. That's a win-win. Now, one area where I've heard nanocatalysis is making a splash is in these things called biorefineries.
Oh yeah, biorefineries are fascinating. Basically, they're like factories that take stuff like wood or leftover crops and, well, turn them into something useful.
So we're talking about moving away from oil and all that.
Exactly. Biorefineries could be a huge part of a more, let's say, circular way of making things.
Sounds promising. But I've heard that dealing with something called lignocellulose, which I guess is in a lot of plants, is a big challenge for biorefineries. Is nanocatalysis helping with that?
It is. That's one of the exciting parts. Nanocatalysts can be designed to break down that tough lignocellulose, making it much easier to use.
Now, shifting gears a bit, we've got biorefineries using nanocatalysis, but it can also be used to tackle a much bigger issue, right? I'm talking about CO2.
Oh, absolutely. That's another huge area of research, figuring out how to use nanocatalysts to capture and, even better, actually use CO2.
Like turn pollution into something useful.
Yeah.
And that would be incredible. But before we go too deep into the applications, I'm curious about the nanocatalysts themselves. What are they made of? What are they like?
Think of it like this. You've got these tiny chefs, the nanoparticles, working on a big kitchen counter, which is the support material.
Okay, so there's more to it than just the nanoparticles themselves. This support material is important too.
Crucial. It needs to be tough, able to handle the heat, literally in some cases, and keep those tiny chefs from clumping together. We call that sintering, and it's a big no-no for efficiency.
So keeping those tiny chefs happy and spread out is key. But how does all this actually work? What's going on at that tiny, tiny level that makes nanocatalysts so effective?
It all starts with adsorption, which is basically when the molecules involved in a reaction kind of latch onto the surface of the nanocatalyst.
Like they find their little parking spots.
You could think of it that way. And there are different types of adsorption, some strong, some weak, and that determines how the reaction will go.
So the nanocatalyst isn't just sitting there, it's actually playing a role in how things interact. It's like a tiny matchmaker for molecules.
A matchmaker, that's a good way to put it. And how those molecules connect to the catalyst, whether it's a strong bond or a weak one, makes all the difference in the world.
This is blowing my mind. So much happening at a level we can't even see.
Right. That's why understanding these basic processes is so crucial. It's the key to unlocking the true potential of nanocatalysis.
So we've got these molecules, they found their parking spots, they're all cozy on the catalyst. What happens next?
Well, think of the nanocatalyst surface like a dance floor.
Okay, the dance floor, I like it.
Yeah. So the molecules, they're energized now, right? They start interacting, bumping into each other, forming new bonds. That's where those new products are made, right there on the dance floor.
So it's like a molecular square dance, all thanks to the catalyst.
Exactly. And just like any good dance, it's a cycle, right? Once the new molecules are formed, they kind of, they do-sa-do off the dance floor.
Do-si-do, I love it. So they make room for new molecules to come in, and the whole thing starts again.
Exactly. It's a constant cycle of adsorption, reaction, and then desorption. That's what we call it when the new molecules detach.
So basically, the nanocatalyst is this non-stop party host, making sure the molecular dance floor is always hopping.
That's a great way to put it. And that's why catalysis in general is so important, you know?
Yeah, I mean, we've been talking about all the cool stuff nanocatalysis can do, but it seems like regular catalysts are pretty important too, right?
Absolutely. They're the workhorses of so many industries. They speed things up, they make reactions more efficient, and they help to reduce waste.
So even without the nano, catalysts are already doing a lot of good. But of course, nanocatalysis takes things to a whole new level, right?
Oh, for sure. The level of control and precision we have with nanocatalysts is just, well, it's amazing. It really opens up a whole new world of possibilities.
Speaking of possibilities,
Yeah.
where do we go from here? What are the big challenges, the big questions that researchers are trying to answer?
Well, one thing that's kind of a bottleneck right now is that a lot of catalyst design is still very trial and error.
Really? So it's like throw a bunch of stuff together and see what sticks.
It's a bit more sophisticated than that, but you get the idea. To really push the field forward, we need to get better at designing catalysts from the ground up.
So understanding the why behind what works, not just the what.
Precisely. We need to dig deeper, figure out the exact mechanisms, the atomic level interactions that make these catalysts tick.
Now, going back to something you mentioned earlier about gold being a catalyst, I thought gold was like inert,
Yeah.
that doesn't react with much.
Right, exactly. That's what makes it so interesting. When you get gold down to the nanoscale, it actually becomes a really good catalyst, especially for certain types of reactions.
So it's like gold has this hidden superpower that only comes out when it's super tiny.
You could say that. The reason is, well, it's complicated. It has to do with the way the electrons are arranged in a gold nanoparticle and how that affects its ability to interact with other molecules.
So the size and shape of the nanoparticle really matter.
They matter a lot. And here's another thing. Remember that support material we talked about?
The kitchen counter for the tiny chefs.
Yeah. Well, it turns out that the support material can actually influence how well the gold nanoparticle works as a catalyst. It's like a team effort.
So the support material isn't just a passive scaffold. It's an active participant in the whole process.
Absolutely. And that's another area where there's a lot of research going on, trying to find the best combinations of nanoparticles and support materials for specific applications.
Sounds like there's still a lot to learn about this whole nanocatalysis thing.
Yeah, tons. But that's what makes it so exciting, right? It's a field with so much potential, and we're only just beginning to explore it.
Now, I know we've been talking a lot about the general principles of nanocatalysis, but let's bring it back to something a bit more concrete, something with local relevance. We mentioned earlier that Finland has some pretty ambitious goals when it comes to sustainability, right?
Right. Aiming for carbon neutrality by 2035, which is, well, pretty ambitious.
It is. And I understand that Finland is already a leader in biomass technology. Is nanocatalysis playing a role in all of this?
Oh, absolutely. I mean, Finland has this long history with forestry, right? So they're really good at using wood in all sorts of ways. And now they're applying that expertise to biorefineries.
So taking those biorefineries we talked about earlier and making them even better with nanocatalysis.
Exactly. The goal is to go beyond just biofuels, to use wood and other biomass to make all kinds of things like bioplastics, chemicals, even food ingredients.
Wow. So we're talking about replacing a lot of the stuff we get from oil with stuff we can grow.
That's the idea. And nanocatalysts are crucial for making those processes more efficient and cost-effective.
But I imagine working with biomass is, well, pretty challenging, right? It's not as simple as just refining oil.
It's definitely more complex. Biomass is made up of all these different molecules, each with its own quirks. You need the right tools to break it down and extract the valuable stuff.
And those tools are, you guessed it, nanocatalysts.
Bingo. They allow us to be very specific about which molecules we target, which reactions we want to happen.
So it's not just a blunt instrument. It's a very precise way to control the chemistry of biomass.
Precisely. And that's why Finland is so focused on nanocatalysis research. They see it as a key technology for a sustainable future.
Now, before we completely run out of time, we need to talk more about CO2 reduction. It's such a big topic, and we only briefly touched on it earlier.
Oh, right, yeah. It's definitely one of the most exciting areas where nanocatalysis could make a huge difference.
So how exactly can nanocatalysts help us deal with this whole climate change thing? I mean, we're talking about a global problem here.
Well, for starters, they can help us move away from fossil fuels. Think about solar cells, fuel cells, even better batteries. Nanocatalysts can make all of these technologies more efficient.
So powering our world with cleaner energy, that's a good start. But what about the CO2 that's already out there? Can nanocatalysts help us with that too?
They can. That's what I was talking about before, the idea of capturing and converting CO2.
So not just reducing how much we emit, but actually cleaning up the mess we've already made.
Exactly. Researchers are working on nanocatalysts that can literally suck CO2 out of the air or from industrial emissions and turn it into something useful.
Like what? What can you make out of CO2?
Well, potentially a lot of things. Fuels, chemicals, building materials even. It's all about finding the right catalysts and the right reactions.
So we're talking about turning pollution into products, essentially.
That's the idea. It's a big challenge, of course. We
Yeah.
need catalysts that are efficient, that are selective, and that can be produced on a large scale.
Sounds like a tall order.
It is, but the potential payoff is enormous. I mean, if we can make this work, we're talking about solving one of the biggest problems facing humanity. It's definitely worth the effort.
It's mind-blowing, really. This tiny thing, a nanocatalyst, could be a key to tackling climate change. Talk about the power of science.
It's pretty remarkable. And you know what's even more exciting? We're really just getting started with nanocatalysis. Who knows what we'll be able to do in the future?
That's what I love about science. Always pushing the boundaries, always discovering something new.
Exactly. With nanocatalysis, we're basically working with matter at the most fundamental level. The possibilities, well, they're almost endless.
Okay, before we wrap things up, let's do a quick recap of what we've learned in this deep dive into the world of nanocatalysis.
We've seen how these tiny particles can do some pretty amazing things. Speed up reactions, make things more efficient, help us use resources that are, well, sustainable.
We talked about biorefineries, how nanocatalysts are making them even more effective at turning plants into, well, pretty much anything.
And we went deep, literally, into the catalytic cycle itself, understanding how these tiny particles act like, what did you call them? Tiny chefs, orchestrating reactions at the atomic level.
It's incredible how something so small can have such a big impact. So as we close out this deep dive, I have to ask, what other challenges do you think nanocatalysis could help us overcome?
Ooh, that's a good one. Well, one thing that comes to mind is environmental remediation, cleaning up pollution, getting rid of toxins in our soil and water.
Yeah, that's a huge issue, and it's only getting worse.
Right, exactly. And I think nanocatalysis could be a game changer there. Oh, and another thing, clean water.
Clean water.
Yeah, I mean, access to clean water is already a problem in many parts of the world, and it's only going to get more challenging as the population grows and climate change intensifies.
So nanocatalysts could be used to purify water more efficiently.
Exactly. There are already some promising technologies being developed.
Wow, that's really exciting. It's inspiring to think that something so small could have such a huge positive impact on the world.
I agree. It gives me hope for the future.
Well, that brings us to the end of our deep dive into nanocatalysis. I don't know about you, but I've learned a ton today.
Me too. It's been a fascinating conversation.
And to all of you listening, thank you for joining us on this journey into the nanoscale. Who knows, maybe one of you will be the one to make the next big breakthrough in nanocatalysis. Until next time, keep exploring and stay curious.